Okay, so I've received a couple of questions that I want to clarify. I want to make sure that we're understanding because it seems like whenever I've tried to do these things in class, I might have stopped just shy of completely explaining it. So let me try to get my document camera out here. Okay, that is not the right direction. I'm trying to zoom out. Now you guys can see my knuckle. Oh, there we go. My whole hand. Okay, give it a second, it'll come into focus, and I'll show you what I wanted to show. It had to do with proving big omega, because I think every time I've tried to show you something with big omega, I've probably stopped just shy of perhaps something critical. So I'm going to talk about your homework problem that involved big omega, and it was, let me try to dig it up. Where is that homework problem? It was one of the problems from chapter 3 of your book. Said prove, well, I can remember it. You have some p, polynomial p of n equals the sum from I equals 0 to d of a sub I n to the d, and you're also given that a sub d is greater than 1, right? Yeah, and you want to show that, so you're asked to show a couple of things. And one of the things you're asked to show is that p of n is omega of n to the, well, they say k, where k is less than or equal to d. And I think because of the way omega works, it suffices to show, and so that's all I'm going to do, that p of n is omega n to the d. Hang on a second. Somebody's at my door. I guess not. Okay. So I kind of wanted to get through this kind of proof because you're going to have to know things like this. So the first thing that we want to do is we kind of want to restate this as an inequality. So what we're really trying to show is that the sum from I equals 0 to d of a sub I n to the d, and because we're doing big omega, we want to show that it is greater than or equal to, and then I'm going to, just save space. The thing that we want to show it's greater than or equal to eventually down here is some c times n to the d. And the trick is how we get from here down to here. So the actual inequality is this is greater than or equal to that. And before I used the trick that, well, for one thing is we could pluck out the higher order term, and I used that to prove big O. And in the last video, I kind of showed that, oh, for big omega, you have to make sure that your constant is positive, but you can fix that with n naught. But I didn't show you how to fix it with n naught. And so in this video, I kind of want to show you how you can address that with n. So again, repeating the same thing that we did for the proof of big O, this is going to be greater than or equal to a sub d n to the d, so you can just pull that out. And in this case, since we're doing an upper bound, we want to make a choice that shrinks it. I'm going to start by showing something that this is equal to. So it's equal to that plus the sum from I equals 0 to d minus 1 of a sub I n to the I. And the trick is there is a thing that we did that made this bigger, which was we replaced all of the a's by their absolute values, and then we raised n to a higher power. I'll show you that in 2 steps. So this is going to be greater than or equal to a sub d n to the dth power. And since we're going to make this bigger, what we really want to do is subtract its absolute value in it. So what we're going to do is we're going to subtract the sum from I equals 0 to d minus 1 of the absolute value of a sub I. And remember, the absolute value of a sub I is always going to be bigger than a sub I or equal. And so by subtracting it, we make sure that this thing is always less or equal and I could just write the n to the I. So again, now we can actually make this thing even smaller. Remember, we're trying to make it smaller at every step by replacing that n to the I by an n to the, say, an n to the d. So this is equal to a sub d, n to the dth power, minus, and now we have a sum, and I'm not going to write the limits because we remember what they are and I'm running out of space, of the absolute value of a sub I, n to the d, and this works whenever n is greater than or equal. So we've got our first kind of limit on n naught. And so we can factor these things out, right? So this whole thing equals a sub d, and then remember this n to the d, it can be factored out of that, right? That n to the d, because it doesn't depend on what, you're iterating over I, right? So the n doesn't depend on I. You can pull that n out. So this is a to the d, a sub d minus that summation of a sub I, all times n to the d, and we would be happy here saying that's greater than or equal to c times n to the d. We would just set c to this. But the problem is it's quite possible that this is negative, and your constant c needs to be positive, right? So let me just kind of indicate here, this might be negative, right? Could be negative. Or equal to 0. You can't even have it be equal to 0, right? Because part of the definition of big omega is that there exists some constant greater than 0. It can't be equal. So we need to figure out how we can kind of fix this to keep it positive. And I think the trick is that all the way over here, I think what we can do is we can kind of pick a value for n naught. So let's suppose that right here, instead of saying n greater than or equal to 1, we could actually remember we're multiplying by an extra, the highest order term. Let me cover some of this up. We're right here in the process, right? And so this is going to be greater than or equal to a sub d n to the d minus, and instead of raising this I to be n to the d, we could raise it to be n to the d minus 1. So again, it's minus the sum over your i's of a sub I. But instead of multiplying it, instead of making that thing be n to the d, I could make it be n to the d minus 1, because that's kind of the maximum value it's going to be. It's still perfectly legit. But instead of currying everything to have all d's there, I can have a d minus 1. And still, I can factor this piece out. Right? Now the trick is I can say that this is greater than or equal to, and I can kind of multiply by n divided by n naught over here. So this is a sub d, n to the d, minus, and then again, still keeping this thing, that part bigger, which makes the whole thing smaller. I can take n divided by n naught times that whole constant thing in there, times n raised to the power d minus 1. That's a perfectly legit thing to do, and that will be true as long as n is greater than or equal to whatever I pick for n naught. Okay, so I get a little bit of freedom here, right? And that way n naught can be used to shrink the effect of this constant. So this is equal to a sub d, and I'm factoring out n to the d because this n times that n to the d minus 1. Let me not factor out yet. I'll do it in multiple steps. A sub d n to the d minus, and then I'll write that summation, summing over I, divided by n naught times n to the d minus 1 times n is n to the d. So now I've got this as sort of my constant. And this is equal to, if I factor out the n to the d's, a sub d minus that sum over I of a sub I divided by this, whatever I pick for n naught, times n to the d, and that is equal to c times n to the d if c is equal to a sub d minus that summation. The trick is I need this to be positive, and so I need to figure out what values of n naught keep c positive, right? So to keep c positive, remember, that's the whole reason we introduced this sort of degree of freedom here. So we want to say that we need a sub d to keep c positive. That means that a sub d is bigger than this. So we need a sub d must be bigger than the sum of the a sub i's divided by n naught. So what we can do is we can just set n, we say n naught must be bigger than the sum of all of the a sub i's divided by a sub, still with the absolute. I might have jumped a couple of steps to get there. I believe this line of reasoning is correct. And kind of the trick here is, in order to make it work, and this is what I was maybe obliquely referring to, is it's not enough to choose C, but you also are going to need to constrain what n naught is in order to make your choice for work. Let me try to think about a slightly simpler example. I think I proved something like this, but imagine that you've got something like prove x to the prove n to the d minus n to the d minus 1 is omega. Let's make it more complicated. A minus b is omega n. Right? That's kind of the general formula, which means that you want to say a times n to the d minus b times n to the d minus 1. That should be greater than or equal to, again, at the end, you want it to be greater than or equal to some constant. Right? So in order for that to work, the real trick here is recognizing that you can instead of, this is going to be, you're subtracting. Important to recognize you're subtracting. So you can kind of make a little box over here to explore and recognize that b times n to the d minus 1 is less than or equal to n divided by whatever n naught you want times b times n to the d minus 1, as long as n is greater than or equal to n. Right? right where n equals n naught, this is a 1. Then you've got perfect equality. If n is bigger than n naught, then you're multiplying this by something bigger than 1. How that works? So this thing holds, right? And then that, of course, equals b divided by n naught times n to the d. And that's the trick that we use. Now we're subtracting this over here. So we say a n to the d minus b n to the d minus 1 is going to be bigger. This is getting subtracted out. Then a n to the d minus b over whatever choice we pick for n naught. We just kind of used that, right? And that is, of course, equal to, if we factor it out, a minus b divided by n naught times n to the d. And because we can now choose n naught, we can solve for the value of n naught that would keep our constant positive. Because this is basically what our constant is, right? So but we've got an extra condition. If c equals, I'll put it down here. If c equals a minus b over n naught, and now we need to choose an n naught that keeps this positive, and so basically we need n naught needs to be equal to. So remember, c needs to be positive. So a minus b over n naught must be greater than 0. So you can do whatever algebra you want to. Remember, n naught is positive, and I'm assuming that a was positive here too. So that means that we can do something like I don't know why I'm mentally hiccuping right now. We can subtract this, or we can add this to both sides. So a has to be greater than b over n naught, and we can multiply both sides by n naught. So a n naught must be greater than b, and then of course we can divide both. A n naught should be greater, right? And that's the exact pattern we just saw. So if n naught is greater than, okay, so this would be another omega proof that works. It's the same idea as what you could use for your problem in your book. So try to test yourself, see if you can solve problems like this one. That would be good for you to